Okay everyone, here's an example, and it's really one of the few that I can do from the earlier sections where we're just looking at our stress-strain diagram. So you're given a stress-strain curve right here, and it says find the modulus of elasticity E. Now, I would say take a few minutes to do this, but it's actually a fairly simple problem, because our modulus of elasticity E is just the slope. It's the slope of the linear section of the line. So if you can find any 2 points, we know one of them, which is just 0, and a second point, which was given right here, and you take the slope, which is rise over run, you can solve for it. So your modulus of elasticity in this linear section, which is the only place you can calculate it, would be my change in the stress over the change in the strain, which will be 43.5 KSI per 0.0041 inch per inch. Remember, that's not really a unit, so it'll just have units of KSI. And it comes out to be 10,610 KSI. And that's it. You're done. It's amazing, I know. Okay, but that's only a minute long, so we're going to go ahead and do the second example together now as well, just so you get some more experience. So here's a bit harder example. A lot more going on, but still dealing with strain. So what we have here is rigid bar ABC. That's this long bar right here. It's supported by a pin A and a 100 millimeter wide by 6 millimeter thick aluminum alloy bar at B. Okay, right here. Before load P is applied to the rigid bar at C, load right there, okay, the strain gauge measures 0 longitudinal strain at an ambient temperature of 20 degrees Celsius. After load P is applied to the rigid bar at C, and the temperature drops to -10 degrees Celsius, a longitudinal strain of 2400 microstrains is measured in the aluminum bar. One thing to remember here is that this is a rigid bar ABC. A rigid bar ABC. That doesn't change. However, our bar from our vertical bar, the vertical aluminum bar that's supporting the rigid bar, is not rigid. It can change. So what we're asked to find is the stress in member 1, this vertical aluminum bar, and the magnitude of the load at P. So, as always, I want to give you a few minutes to try this on your own, so please pause, then come back and you tell me how it went, okay? Once again, just do that when no one's around, because this is a video and you'll just be talking to your computer. Pretend like you're Skyping. You know what that works? Pretend like you're Skyping. No one will even judge you then. Okay, so pause, try it out, then come on back. 3, 2, 1, and you're back. It went wonderfully, it went terribly. Well, we're all about to find out. So first off, you need to calculate the stress. Okay, so we know that stress is equal to the modulus elasticity times the strain. And so we know what the strain is at the end. We also know what the modulus elasticity is. That'll be 168 megapascals. But that was wrong. Thermal strain reduced the total normal strain measured. You're like, wait, what's going on here? Think about it this way. I have a bar. If I pull down on it, it gets longer. If it gets cold though, cold, it gets shorter. So those are canceling each other out a little bit when it's just coming to strain. You gotta think about this. So both effects are going to be added in to that strain we measured right here. So let's look at it again. So first off, let's calculate that thermal strain. Well, we have our modulus elasticity, which is 22.5 times 10 to the -6 per degree Celsius. We have a temperature change of -30 degrees Celsius. And so that would be a thermal strain of -6.75 times 10 to the -4 microstrains. Okay. And that is negative, so it means that whatever our strain was, it is going to be greater, would have been greater than our 2.4 times 10 to the -3 strains if we hadn't had that temperature change. So now we're going to calculate the normal strain. So the 2.4 times 10 to the -3 strains we saw before, or 2400 microstrains we saw before, that would be the total strain. So we subtract off our thermal strain. What we'll get is 3,075 microstrains, or 3.075 times 10 to the negative third strains. Now with that, we can calculate the stress that did that. So stress is equal to our strain times our modulus elasticity. So 70 times 10 to the 9th gigapascals, multiplied by our normal strain. It's going to be 215.3 megapascals. And then from that, we can calculate the load that would cause such a stress. We know what the cross section is, and so we can solve. The answer comes out to be 129 kilonewtons. Then finally, using some limits around point A, we can calculate the load, because what we saw right here is the force that would be pulling on my particular point on that bar that's holding it stationary. And we have to then figure out what was the load at the end that would cause that. So we're taking some moments around this point. So we do that, and we come out to be that the load will be 77.5 kilonewtons. 77.5 kilonewtons. So I hope this helps you, and hope it makes sense. Just remember, you got to take into account all those thermal effects when you're solving your problems. Just think about everything separately. Okay, what would the normal strain be doing, or normal stress be affecting it? How would the temperature be affecting it? How would those add together? What would I expect? And go from there. So thank you for paying attention, and I look forward to seeing you next time. Have a wonderful day. Bye-bye.